I welcome you all to the live interactive session. Today we'll be discussing about cogeneration of power and process heat. So let us start. So let me tell you about this what is cogeneration of power and process heat. So this is a separate arrangement of a Rankine cycle. So in Rankine cycle we primarily focused on generating the power, right? But we did not look at the what will be happening at the condenser section. So in the condenser section we are releasing a lot of heat, right? But why not we can utilize it, right? So there are some processes, heat treatment processes in various industries like paper mills, textile industries, just getting chemical factories, jute mills, sugar factories, rice mills, like this kind of processes where heat treatment is required, and uh, isothermal conditions can be maintained by allowing the saturated steam to condense at the temperature and utilizing the latent heat release, because if the steam is in saturated condition and when it condenses, so it will be maintaining a constant temperature, and we can go for constant temperature processes, heat treatment processes, just like the steam used in textile mills. So that is the purpose of this saturated steam, so which can be derived from the boiler. But okay, these factories also require power to drive various machines, right? So for lighting and other purposes. So they why not means combine the both things. Previously what happened was that the steam was produced at separately in the boiler, and then power was also produced separately at moderate pressure. So both of these systems were operating separately. That is why it was a wasteful resource. But the concept of cogeneration plant came, where it is a plant which produces both electrical power and process heat simultaneously. So the heat rejected in the condenser section at constant temperature, it will be utilized for process heat. And I'll be talking in this lecture about how this plant is working, and will be solving a few more problems, which will also give you an insight how to solve other problems. It will make you more comfortable with the Rankine cycle and other processes. So I'll be referring to the book Power Plant Engineering by P.K. Nag, and you will find this section in page number 78 of this book. So cogeneration of power can be and process heat can be done by two processes, of which the first one is using a back pressure turbine. So here I am showing you the schematic. It is a very simple arrangement, and the maintenance cost, also the setting of cost, these are very less. It's a very simple means schematic also. So here you can see that the condenser section, so at the outlet of this turbine, this is the turbine, this is the boiler. So from the boiler the steam is generated, this is the inlet to the turbine, and from the turbine it is going to the not to the condenser. The condenser is replaced by the process heater segment. So here the various processes wherein the heat treatment process is required, it will be providing the steam to that sections, and from there the pump will take up the feed water at this wet conditions, the water which has condensed, and it will again supply to the boiler. So the condenser is removed and the process heater is replaced in this part. And but there is one thing that we'll have to take care of: the inlet to the turbine. So the inlet initial steam pressure and turbine exhaust pressure are to be modified to generate the required power, along with supplying the steam at the saturated conditions. So by inlet to the turbine I mean this particular point, the point 1. So 4 to 1 is the process of heating the water in a boiler and generating the steam, right? So from 1 there will be this generally it is an isentropic process, a reversible adiabatic process in a turbine. But in real life you will never find a reversible process, and be it a reversible adiabatic process. So you will always find that this curve does not go vertically downwards, but it will go a slanting downwards. So generally I'll be talking more about this efficiency and why this curve is going this way. I will be talking more with the help of a HS diagram. But let us now proceed further. So the back pressure turbine, actually what it means is that the pressure at the exhaust from the turbine is the saturation pressure corresponding to the temperature desired in the process heater. This means, suppose this is a TS diagram, so the 3 to 2 process, the 2 to 3 process, it is at constant temperature, right? It is condensing. So if at this temperature we need the process, the heat treatment process, so we will be supplying the turbine or supplying the steam from the turbine from the point 2, that is a saturated condition. So we'll be applying some pressure, we'll be not allowing the expansion properly of the steam inside the turbine. We'll be restricting towards the end. That is why we are supplying some back pressure to the turbine. So that is why the name back pressure turbine came. So generally this process would have gone here till this pressure point, but now we have restricted that and we have given some back pressure so that the process stops or the expansion in the turbine stops at point 2, so that we get a saturated steam condition, and then from there the process heat part will take on. So that is why the back pressure turbine name came from. Then such cogeneration of power and process heat, this is also called as a byproduct power cycle, because the process steam is the basic need, but the power is produced incidentally or as a byproduct. So actually in these mills the process heat was the main the main desired effect that we needed, right? But on getting this, we are also getting the power to run other equipments. That is why it is called as a byproduct power cycle also. Now looking from the TS diagram, we will agree that the work generated from the turbine, that is from 1 to 2. Okay, so that will be WT equals to WS. See, this is the rate of flow of steam through the turbine. So WS into H1 minus H2, the enthalpy difference between the inlet and the exit part of the turbine. Then the process heat utilized, it will be this part, right? In the condenser, we are actually treating to the means the segments where the steam is required or the heat treatment process is required. So the QH is directly going to that segment. So the process heat utilized is from point 2 to point 3. So it is the process is extracting the heat from the steam at this isothermal condition, and subsequently the dry steam is getting converted into wet steam, and finally to water. The whole of the latent heat is being used. So that is the process heat being utilized, which will be given as WS into H2 minus H3, the enthalpy difference between H2 and H3. Then we have the efficiency of the turbine. So I was talking that this curve is a little bit slanting, right? 1 to 2. Not 1 to 2 dash, which is vertical or isentropic process. So that is why the point 2 is at a higher enthalpy than point 2s, state 2s. In the turbine, due to some losses, the enthalpy difference in the turbine, actually it has been reduced, right? Since 2 is at higher enthalpy, so H1 minus H2 will be lesser than H1 minus H2s. That means H1 minus H2, it will be less than H1 minus H2s. We needed this state, isentropic state, but we are not getting, rather we are getting H1 minus H2. So there is some difference due to which we have a particular efficiency called as the efficiency of the turbine. Later on I will be explaining this with HS diagram, so you need not get worried about it. I will be explaining it with at different pressure locations, how the pump and the turbine can be characterized in terms of efficiencies. So as I have said, H1 to H2s, this is an ideal isentropic process, this vertical ideal isentropic process, reversible adiabatic process. But H1 to H2, that is this is a real reversible adiabatic process, irreversible adiabatic process. That is why we are representing this line with dotted or dashed line. So in all the TS diagram or HS diagram, so if we have a irreversible process, irreversible. That is from 1 to 2 if we go, then we cannot come from 2 to 1 without expending some amount of work. We can obviously come from 2 to 1, but we need to give some work. We cannot come from directly from 2 to 1. So these are irreversible processes, and these processes are represented by dotted lines, as you can see here. So this may be due to the insulation loss or the entropy. That is why the entropy always increases from 2s to 2. You can see out here. So now let us move on. Can we really derive the QH in terms of work of turbine? So you can see here the work of turbine and the QH is being correlated. How can we correlate it? So WS, in both this equation, the WS is a constant term. So we have simply eliminated this WS as QH by the H2 by H3 here, and multiplied by H1 minus H2, which was previously here. So that's how we got QH equals to WT into 3600 into H2 minus H3 divided by H1 minus H2. So why this 3600 is coming? Generally we have work of turbine in kilowatt, right, or kilojoule per second. So if we need the unit in kilojoule per hour, we'll have to multiply it with 3600. So the second is in denominator, right? So that is 1 by 3600. So it will go to the numerator and it will be multiplied. Then I was talking about the desired effect, right? So using that, we will be relating the efficiency of the cogeneration plant. So the efficiency of cogeneration plant, like any other efficiency, it is the desired effect by the heat supplied. So desired effect here, since we are utilizing this QH work, which was not previously utilized in normal Rankine cycles that we have studied. So here QH is being utilized in desired work. Also the WT, we are getting some work from the turbine also. So these two are the desired work. So that is why we have added this WT plus QH, and we have divided it by heat supply, that is Q1. So this is the efficiency of a cogeneration plant. And you can see from the schematic also, from second law, we can say the work of pump is being supplied to this system. Source is delivering Q1 heat. So Q1 is delivering into the boiler. Then the QH is actually was going to the sink, but the sink now is the process heater or the heat treatment plants. So we are utilizing this QH, and also the work of turbine is also utilized. That is why the efficiency is being said as like this. From the second law, we can say like this. Next, I will be talking about how can we really assure that whatever we are co-generating, that would be very good, or should we have produced separately the process heat and the electricity. So how can we characterize that we are doing a very good work? Okay, so we are co-generating and we are doing a very good work. So how can we say, how can we qualitatively say that? So for doing that, we first will take out the efficiencies of both the processes, right? So for we already discussed the cogeneration efficiency, but now let us talk about how to derive the separate efficiency of a case where separately the process heat and the electricity are produced. So this is the schematic of the process heat generation. The source will give some heat to the system, so some amount of work or some amount of energy will be lost, and then the QH will be given to the process heat, that will be the sink. Okay, so this is generally the waste work done or the efficiency losses, because the heat will be supplied from one point to the other, right? Then in electricity generation, again we draw the second law schematic. So this is the source, it will deliver a Q1E amount of heat to the system, and it will impart the work WT, means from the turbine we are generating this amount of work, and QL is being delivered to the sink, which we are not utilizing since we are separately producing the both, right? So we are utilizing the QH from the process heat generation and WT from electricity generation unit. Okay, so the efficiency in both the cases are the eta H is QH by Q1H. So how can we get that? So this was the desired effect, right, in process heat generation. and this was the heat supply. So QH divided by Q1H, that is the efficiency of process heat generation. Then electricity generation, so that is we are supplying Q1E of heat, that is why it will be in the denominator, and WT is the desired effect. We are actually producing the electricity, we are not concerned about the QL, the loss to the sink. So the efficiency will be given as like this: how much amount of electricity can we produce by supplying this amount of heat energy. So that is the efficiency, right? So how much amount of heat can we reject to the heat treatment process by supplying Q1H amount of heat to the boiler. So that is the efficiency of process heat generation. Now we will all agree that the total heat supplied in both the cases will be Q1E plus Q1H. That will be so from this we can actually by doing some manipulation we can write WT by eta E and QH by eta H. So that will be the total heat supplied, right? So the heat supplied per unit total energy, so this should be unit, sorry, so unit total energy output. So what is the total energy we are getting? We are getting the QH to the process treatment, the heat treatment processes, sorry, and the electricity generated, WT. So these are the total heat total energy we are getting as output, right? So Q1 per WT plus QH. So we will be writing it as, so WT by WT plus QH and QH by WT plus QH. So here we will be using one term as electricity fraction of the total energy output. This is nothing but we are just arranging this as E. Okay, since it will be a very big term, so we'll be simplifying it by keeping E equals to WT by WT plus QH. So like that, if we do some arrangements, so we will find that, so this will be given as E, and this we will simply plus and minus the WT term, and by dividing we will get 1 minus E. Is there anyone having any doubt? Anyone having any questions till now, or am I getting too fast? Okay, then I will assume that there is no doubt. Let us move on. So this will be the heat supplied per unit total energy output when for the case of separately produced process heat and electricity. Okay, separately produced. Then the combined efficiency of these two processes, this process and this process, will be given by this, that is WT plus QH, right? That is the total desired effect, the desired output that we want, and the total amount of heat we are supplying, Q1. So that will be given as this. So now we will have to see whether by cogeneration the efficiency of the cogeneration is a little bit less. Means the cogeneration having higher efficiency. The cogeneration, if it is having higher efficiency than the combined efficiency, means if we are actually combining the cogenerating in the same cycle the power and the process heat, rather we are not doing like this, that we are separately producing the electricity or separately producing the heat and heat generation. So if the cogeneration efficiency is higher than the combined efficiency, then we can actually go for that cogeneration plant. But if it is not, suppose I will give you an example. Suppose if you need a very small scale miniaturized power plant, okay, if you have a miniaturized some heat treatment plant, okay, then we may not go for cogeneration. So cogeneration will give us a lot of lesser efficiency. So this is the criteria based on which either we should go for cogeneration or we should opt for separate production of process heat and electricity. Okay, so next we have talked about the first this process of cogeneration, that is this back pressure turbine. Now we will be talking about the another type of turbine, this is pass out turbine. So why are we talking about the turbines? Because from the turbine exhaust we are delivering the steam, right? So there can be various methods of delivering the steam from the turbine exhaust. So the first one was back pressure turbine, the second one is the pass out turbine. Now this is the schematic, but first I will tell you why do we need to go to pass out turbine, or what are the limitations of back pressure turbine. So the power output from the back pressure turbine, that may be very less, because we are actually limiting the range of the this expansion, right? We are limiting the range, we are not allowing the full expansion of the gas, so in order to get the dry steam at a particular pressure condition. That is why the power output may be very less. That is because of the high back pressure, or because of very small heat requirement. So by this, what do I mean? So we are utilizing the latent heat, right? So suppose the latent heat, you might be knowing that as the temperature increases, the latent heat also decreases, right? The latent heat decreases. So if the if the heat requirement is small, then we will be preferring at a higher temperature the latent heat. The energy exchange should be less, right? So we will be inducing more back pressure to the turbine to get the saturated condition in that state. That is why this is also one condition. Then this is unable to supply the power to run other plant equipment. So if the power output is less, so it may not be able to supply power. So these are the limitations of back pressure turbine. That is why we have the scientists have come with another innovation. So this is a pass out turbine. So although the complexity is a little bit more, but here are the advantages. So a certain quantity of steam is continuously extracted from the turbine at an intermediate stage for heating purposes at desired temperature and pressure. So what it says is that, so we have a turbine here. Okay, so turbine inlet is here. From the boiler, it is being inlet at this point, the steam. So in normally the whole of the steam is getting expanded, right? But we are extracting some amount of steam from intermediate stage of the turbine through this process that you can see, and this process will be going to the process heater. This steam through this process will be going to the process heater, and accordingly it will the condensed water will be again pumped back to the boiler. Then the steam which has already expanded to the full capacity, we are not inducing any back pressure, we are not limiting the exit conditions, so that will be going to the condenser, and the heat will be rejected to the condenser, and from there to the pump, and the pump will be delivering it back to the boiler. So that is the whole case. Okay, there is one more case in 8 that I will be speaking of, but till now this is the case. So in a TS diagram it looks like this. So you see that the one is the condition of the inlet steam. The inlet steam, it is being expanded inside the turbine. So this 1 to 3 is the entire turbine expansion. Okay, but in 2, when it is actually reaching the saturated condition, we are actually extracting some amount of steam, the W amount of steam from this turbine, and we are utilizing the heat energy into process heat. You see the QH is being done in here, and the remaining of the steam is expanded to 0.3, and it is later on the heat energy is rejected to the condenser, and it is going back to 4, which is the wet state, saturated wet condition. So the 0.4 and 0.6 is the inlet of the pump. You see the 6 is the inlet of pump 2 here, and the 4 is the inlet of pump 1 here. Okay, so these are actually providing some pressure, doing some work to increase the pressure of the feed water, and then the steams of both the the water from both the steps are mixed together, and final position will be 8. Final state of the water will be 8, because the enthalpy of this 5, it is a bit less, yet enthalpy of the 7, the water at state 7, it is a bit high. Okay, so when we mix, it will be in the intermediate position. The enthalpy will be in between the two. So this is the final enthalpy from which it is heated in the boiler. Okay, so this is point 8, state 8, and state 8 is the inlet to the boiler. So this is being done in the pass out turbine, and it has accordingly the advantage that is high power generation, because the 1 to 3, it is a wide a pressure difference, right? The enthalpy difference is higher now, but the 2, usually we were limiting the exhaust of the turbine to 0.2 so as to get the saturated saturated steam for the process heating. But here we are not limiting, we are allowing the steam to expand, we are just extracting some amount of heat. So that is why it is expanding to the full limit, so we are getting higher power generation here. So that is the advantage. Now from the TS diagram we can deduce the following things. So WT, that is the work of the turbine, it is WS H1 minus H2, so H1 minus H2 plus into WS, the whole of the steam was going, and some amount of steam left out, right? So the remaining amount of steam into the enthalpy difference, H2 minus H3, that is the work generated from the turbine. According the process heat utilized, so this is the step where process is being utilized, so 2 to 6, that is why W into H2 minus H6. Input heat energy, so in the boiler it is being input heat is being delivered, so H1 to H8, right? So Ws is the total water flow rate, so that multiplied to the enthalpy difference, rejected to the condenser, so Q2 H3 H4, and the flow rate is Ws minus W, so this will be the product here, H3 minus H4. Then work done by the pump, so pump is also supplying some work, right? So this amount of water is being pumped up from 4 to 5, and W amount of water is pumped from 6 to 7. Okay, so accordingly this is the work done by the pump. And then from 7 and 5 there will be some mixing. So what will the energy equation during the mixing? So that will be given by this W of H1, W into H1, and Ws minus W into H5. So this is the Ws minus W coming and having enthalpy H5. So together it will form Ws, the total, because W and Ws minus W, total will be Ws, and into the enthalpy position of H8. So these equations will be used later to solve the problems. That is why I am showing it like this for now. So we have learned about this back pressure turbine and this pass out turbine. So is there any doubt till now? Is there any doubts, or is there any queries? Some means you can also go for any other suggestions also, we can discuss in here. Please. Is there any doubt? No doubt. Acha, acha. So everyone is getting, I hope. If you are not getting, then please stop me in between. So this is a live interaction, I would be happy to help you out. Please. Right, right. So back pressure, na. So I will give you an example. So suppose you are operating a tap. Okay, you're operating a tap. So from the tank, water tank, it is at full potential. Okay, to the valve. So tap is acting like a valve, na. So at the inlet of the tap, it is at full potential, but you're opening it, the valve, such that you are getting your desired amount of flow rate. You're not opening it completely, then you are getting half the amount of flow rate. So actually you are giving some back pressure to the water. You are not allowing the whole of the water to come out. So this is an example that I am giving you to correlate. Now in this case what happens is that the full potential of the turbine was from 1 going to 2 dash to somewhere like here, right? So this is an intermediate pressure, so, but the lowest pressure was still here. I will tell you in here with this. Huh. See, so here what we did was that we did not stop the pressure exit at the exit of the turbine at point 2, but we allowed the steam to expand a little bit more till low pressure of 3. So that is the full potential of the turbine. So by back pressure means we are not allowing the steam to come out from point 3, rather we are stopping the steam at point 2, the exit of the turbine, and it is the whole of the steam is coming out. So that is the back pressure which we are giving to the turbine. Aha. Right. Generally, what happens is that the turbine it expands to atmospheric conditions, the normal ambient conditions. Okay, so that is the normal. We will have to utilize the whole potential of the steam produced, right? But what we need is that we need a dry steam state. So that is why we are stopping the full expansion by applying some pressure. So by applying some pressure means we are not going to low pressure, actually we are stopping at higher pressure. So that is why we are applying some backward pressure. So this is back pressure. Okay, so it's a very good question. Okay, so if there is no doubts, let us do one exercise so it will give us more clarity on this. So this is a question that I'm taking from power plant engineering by PK Nag. So the example 2.7 you will you will get this question. So a textile factory requires 10 tons of steam. I will give you the actually the diagram is a part of solution, but still I will give you this. So a textile factory, it requires 10 tons per hour of steam for the process heating. So here it requires 10 tons of per hour of steam. Okay, the tons per hour is actually the flow rate at 3 bar saturated. So 3 bar, so which is quite high. Normally it is 1.01 bar na, the ambient condition, but the turbine will go beyond means it will go till 0.06. We will solve one more problem also. So we are stopping it at 3 bar, which is quite high pressure, and the 1000 kilowatt of power. Okay, the 1000 kilowatt of power is also being need to be produced, for which a back pressure of turbine of 70% internal efficiency is to be used. So now I will talk what exactly is the significance of internal efficiency, means this efficiency of turbine. So first, this is W, this is the mass flow rate of steam. So let us convert it, use the units not kilowatt but rather kilojoule per kg. Okay, so we know what is the requirement, 10 tons per hour, and we know the power. Okay, so we will divide and we will get H1 minus H2 is 360 kilojoule per kg. Okay, so this is 100 watt it was producing, and the flow rate is 1000 tons per hour. So we'll convert it into seconds, and then because watt is in joule per second na, so we'll do this unit conversion. Next we will use the steam table to get the saturated steam condition at point 2. So H2 we will derive from this 3 bar condition, so that will be Hg. So H2 will be 2725.3 from the steam table, hence we will put in here, we will get H1. So we know H2 and we will know H1. Now actually we'll need what is the steam condition in 1. So we need to find out what is T1, what is the temperature of the steam in 1, and what is the pressure P1 at which the boiler should means the steam must be inlet. So for that actually we will have to get through the entropy calculations. So how we will do that? First we'll find out this point 2s. Okay, so this is isentropic, right? So if we find out 2s, then the entropy of 1 and 2s will be same. That is why we will find out 2s first. So how? We are given that the efficiency of the turbine is 70%. So what does efficiency mean? So I am showing this a process of turbine. So here generally it is isentropic process, reversible adiabatic, 1 to 2s, but we are somehow designing it such a way that after the efficiency it is actually landing at 2. So you see this is a HS diagram. and this is a constant pressure process. This red lines are constant pressure processes. Okay, so now you will agree that the point 2 is having higher enthalpy than point 2s, right? In normal conditions, the amount of work done, that is will be h1 minus h2s, the difference, it is actually higher in theoretical conditions, but in real conditions, due to some losses, there will be h1 and h2. Also, the entropy will also increase due to some heat losses, heat interactions. So that is why it is a bit curved, and the efficiency formula is given like this. So h1 minus h2, it is the real process of lower difference, and then h1 minus h2s. Similarly, in pump also there will be some efficiency problems, because the pump is also isentropic. We consider it as isentropic, but it is not isentropic. Okay, so what happens is that h3 and h4 dash, this is less. Now why it is less means, in pump we are doing some work on the pump, right, to supply the water, but the work done, it was actually less, but now due to efficiency problem, the work done will be higher, because we'll also have to account for the heat interaction and everything. That is why 4 point is having higher enthalpy than 4s. Accordingly, the efficiency is given as this: h4s minus h3, which is less, and which was the previous case, and divided by h4 minus h3. So this is the efficiency, and you will find in many problems this kind of statements are given. So you will have to find you will have to solve accordingly. Now here we get the point 2s, h2s, the enthalpy at 2s from this, using the efficiency, and that will be 2571.014. So we have the h2s. Now we can calculate what is the dryness fraction at this point 2s, right? So we have h2s, so we know this formula: hf3 plus x times the hf3 and x times of hfg at this pressure. Accordingly, we find out the dryness fraction of the steam in here. So now 1 and 2 dash is an isentropic process, right? So from this dryness fraction, we can simply find out the S1. What is the S1? That is SF3 plus X2S SFG, the entropy till this point. So S1 will be this. Now we know the enthalpy of 1. Do we know the enthalpy of 1? Yes, we know the enthalpy of 1. We know the enthalpy of 1, and we know the entropy of 1. So we will use a Mollier diagram. So let me assume that you haven't heard of the Mollier diagram. So Mollier diagram is actually the graphs which represents enthalpy, entropy, then we have temperature out here, and these are constant pressure lines. The blue color lines are constant pressure lines. This is green color is temperature lines, constant temperature lines, enthalpy in the y-axis, and entropy in the x-axis. So this is a Mollier diagram, and from many experiments they have finally plotted this particular diagram. Okay, so our purpose is very simple. We know the properties enthalpy and entropy. We know enthalpy in the y-axis, entropy and the x-axis. So we simply draw a line out here. We draw a line, straight lines, and we find out the point of intersection. So the point of intersection lies somewhat lesser than 350 degrees Celsius. And where is the, so this will be, let me see the values. So the pressure, so that obviously this is 50. It should be lesser than 50 and greater than 20. So it is 37.3 bar approximately, and the temperature is 344 degrees Celsius, slightly less than 350. So this is 350 degrees Celsius constant line, so slightly less than 350. And you will find some difficulty in finding the exact point. So what you will do is that you will simply interpolate. Interpolate in y direction, interpolate in x direction based on the 350 and 300 degrees Celsius. So 50 and 20 or somewhat like that. So based on that, you will get this conditions in state 1. So that is 37.3 bar and 344 degrees Celsius. So this was an example which states the use of Mollier diagram. Okay, otherwise if you use the steam table, you will not find exactly where it is, right? So you need the Mollier diagram for that. Okay, so let us move to the next problem. According to the time, maybe this will be the last problem. Okay, let us move anyways. So here this is the graph. In a cogeneration plant, the power load is 5.6 megawatt. Okay, the total power generated by the turbine from 1 to 3, that is 5.6 megawatt, and the heating load is 1.163 megawatt. So what we need is from this, right, from the saturated steam, the intermediate pressure process, that will be 1.163 megawatt. Then the steam is generated at 40 bar and 500 degrees Celsius. So this is the constant pressure 40 bar line, and here at 500 degrees Celsius it will be superheated, and then it will be inlet to the turbine. Then it is expanded isentropically through a turbine to a condenser at 0.06 bar. So we are not considering any turbine efficiency. We are just considering that yes, it is an completely theoretical condition of isentropic case. So 1 to 3 is a constant vertical line. So you see the value 0.06 bar, right? So it is going below vacuum. The vacuum will be at below 1.01 bar. So it is going below that, below atmospheric condition. So that is the actual case. So we are not restricting any pressure. That is, we are not applying any back pressure. So this is what? This is a pass out turbine. So the heating load is supplied by extracting the steam from turbine at 2 bar. So which is condensed in the process heater to saturated liquid at 2 bar, and then pump back to the boiler. So at 2, it is extracted from the turbine, the W amount of steam extracted. Then it is the process heat is being done till 0.6 saturated liquid state, and then again pumped back to the boiler. So here actually there is no mixing between the water which is condensed at here, condenser section, and the water which is condensed by the process treatment. So that is why both are actually going parallelly to the boiler and generating the steam. Okay, so here there is no mixing. We do not need to calculate the 0.8, and then from 1 to 8 we do not have to do that. We do not have to means it's a very simple case. So we do not have to calculate any we'll have to neglect the pump work, I think the pump efficiency, I think. So then we'll have to compute the steam generation capacity of the boiler. Okay, how much is the steam generated from this in the boiler, this constant pressure process. Then heat input to the boiler in kilowatt. So how much input we'll have to give, I think. Then the fuel burning rate of the boiler in tons per hour. If the calorific value is given this, and the boiler efficiency is 88%. So some amount of the heat is given to this, so some amount will be lost. That is why there is an efficiency 88%. And what will be the amount of fuel burning rate? So rate at which the fuel should be burnt for a particular heat. Then the heat rejected to the condenser. So heat rejected to the condenser will be from 3 to 4. And then the rate of flow of cooling water in the condenser if the temperature rises 6 degrees Celsius. So actually here the condenser is it is being operated like this, that some amount of cooling water is flowing. Okay, the cooling water will be flowing at a higher temperature because we'll need to cool this, right? So the cooling so it will be at a lower temperature, sorry. The cooling temperature will be a lower temperature. Only then the heat will be transferred from higher to the lower state. Okay, the higher state is this condensing water. So the temperature difference between the cooling water and this condensing steam, it is 6 degrees Celsius. Okay, so that is given. Let us solve this problem now. So first actually we will have to calculate, we will have to find out this Ws and W. So when we calculate this, only then we will get a better idea of how to solve this problem. So first, let us start from point 1. Okay, so this is given at 40 bar and 500 degrees Celsius. From the steam table you will get H1 and S1, the entropy and enthalpy at this particular point. Since it is isentropic, so we know that S1, S2 and S3. Okay, so it is given that it is point 2 is saturated, but there's no problem in checking, right? We can check. So at point 2 the dryness fraction should be 1, right? So can we check that? Really, in 2 bar we can get the this entropy at 2, that is and x2, so SF6, that is the fluid entropy at 6 saturated water condition. So accordingly we will find that x2, which is the dryness fraction out here, it is 1. So it is actually dry and saturated steam. So actually this the information that was given to us, it is actually correct. So we did a quick checking. Okay, then so I minimize this so that you can also look at the question while solving this. So since x2 is 1, so h2 is equal to the hg2 obviously. Then we got the enthalpy at point 2. Then we calculate the h2 minus h6, this part. So this is the process heat part. So that will be simply the HFG at this particular pressure condition. So W is the rate of steam extraction. So W is the rate of steam extraction. WS is the total steam which is inlet to the turbine. And we know the this heating load, right? We know the enthalpy difference. We know what is the actual heating load. So can we derive W? Yes. So we know the formula W into H2 minus H6. So H2 minus H6 into W. That should be the total heating load, right? So from that we get W, which is the rate at which the steam extracted from the pass out turbine for the process heat treatment. That is the this much kg per hour. Okay. So the first we solved the W. Okay. So now let us consider 1 and 3. Okay. So here this is also isentropic, but this is at wet state. So let us calculate the dryness fraction. So from this entropy equation, so we get the dry state, it is 0.84 dry. Then we calculate the enthalpy from this equation. So we know the enthalpy and entropy at this particular point, right? So H3 and H4, so we know the H3 part. Okay, that's good. Next, let us now calculate the total we know the total power, which is 5.6 megawatt, right? 1 to 3 total power generated is 5.6. We know the enthalpy difference at the enthalpy at point state 3, state 2 and state 1, and that is why we can directly put into this formula that the total power generated by the turbine, Ws into H1 minus H2. So H1 minus H2 into Ws plus Ws minus W. So Ws minus W, it is also expanded in the turbine from state 2 to state 3. So that is the into the enthalpy difference between the two. So that is Ws minus W into H2 minus H3. By this, by solving, we already know the value of W. So by there is only one a variable Ws, so we get the value of that. Ws is 16.73 tons per hour. So Ws actually is the amount of steam that is being produced in the boiler and input to the turbine at the inlet. So we got the first answer, steam generation capacity of boiler in tons per hour, that is 16.73. Then we calculate the next is heat input to the boiler in kilowatt, right? So if we get the points state 5 and state 7, and simply if we since it is going parallelly, there is no mixing, so we will just multiply H1 H5 H1 minus H5, this temperature enthalpy difference, into this amount of water, and then H1 minus H7, this enthalpy difference, into W amount of water. So if you can get the state 7 and 5, we will get the total amount of heat the boiler needs to be supplied. Okay, it needs to be supplied to the boiler. So H7 can be calculated by using this formula. So V6 into P40 minus P2 bar. So there is a pressure difference and the pump is doing some work, right? So V6, how much it is doing? So V6 is the specific volume at 4, and it is increasing the pressure from so we are considering this, so this part, okay, from 2 bar to 40 bar it is considering increasing the pressure. So this is the amount of work done by the pump, and then it is being added to the enthalpy of the water from H6 to H7. Similarly, we will also get the H5 by the pump work added to the H4. So accordingly we get the H7 and later we got the H5. So I think this should have been H5 and H4 here, sorry. So H5 would be H7 would be 508.73, H4 5 would be 153.8. So accordingly, when we put the formula put into this formula, we will get the total amount of heat which is being means taken up by the feed water into being in the steam with properties 500 degrees Celsius at 40 bar. So this is the total amount of heat. Okay, so that is 15.11 megawatt. So we got the heat input to the boiler in kilowatt. So in kilowatt we can do that in 15,000 kilowatt. So next is the fuel burning rate. So what we do is that we know the total amount of heat it is receiving by the water, but what is being supplied, we have to consider the efficiency, and then we will get to know about the amount of fuel being burnt here. So exactly that we have done. So Q1 into the amount of fuel into its the calorific value. So this is being after calculating, we get the amount of fuel being burnt is 2.7473 tons per hour. Per hour 2.473 tons is being burnt. That is the rate we got. Okay, then the heat rejected to the condenser. So this part, so H3 we know, H4 we will get from the steam table, no issue. So Ws minus W is the amount of steam passing from 3 to 4. So by this we will get the heat rejected to the condenser, that is 8.367 megawatt. Then we will we are given that we need to find the rate of flow of cooling water in the condenser if the temperature rises 6 degrees. So this is fixed, temperature difference would be 6 degrees Celsius. So then let us consider WC, the water flow rate in condenser. So this is the specific heat capacity of water, and T2 minus T1. So this T2 minus T1 is 6 degrees Celsius, that is given. So accordingly, when we put, we will get this the Q2 is the this we got heat rejected to the condenser. So if we put these values, we will get that it should be 0.333 meter cube per second. So this amount of water should be supplied to cool down the condenser. Okay, okay. So next we'll be doing one more question, and we'll be ending the lecture. So in a power plant, the efficiencies of the electric generator, turbine, boiler, then cycle efficiency, and the overall plant, so these are all given. Okay, the efficiencies are all given. So what percentage of the total electricity generated is consumed in running the auxiliaries? So for that you kindly refer to this schematic. So what happens is, in this boiler, so simply you follow this. So in this boiler, Q1 amount of heat was supplied, so there is some efficiency loss. Then so QS, due to the loss, the QS is being supplied so to the turbine. There is also some efficiency due to which not the entire energy is being converted into turbine. So the WT is being converted after the efficiency. Then the generator, it is going to the generator. Also the generator is having some losses, like this friction loss. It is a moving part, right? The friction loss and everything. So taking that into consideration, from WT the work is reduced, the electrical power is reduced to WG. Okay, then the whole cycle will also have an efficiency. So due to that, the work produced from the generator, extracted from the generator, it will also reduce to WC. So that is from the cycle. Now from the cycle it will go to the auxiliary equipments, and some amount of the amount of work that is being produced from the auxiliary, so that may be lighting the lamp, or powering the means the valves and everything. So these equipments require some power, so that will be WA. Finally that will be WA. So WA will give us the desired effect. So this is the schematic actually. Okay, so finally following this schematic, we will find that the efficiency of the plant will be WA, the final work, divided by the heat supplied, the initial supply of the energy. So if we divide it into segments, we'll find like this, that so everything will be cancelled out. So we are just separating the all the segments here. Accordingly we are given the efficiencies, right? The QS by Q1, simply the boiler efficiency. Turbine is WT by QS. So similarly, it's generator efficiency multiplied to the cycle efficiency and multiplied to the auxiliaries. So here the unknown is eta auxiliary. We do not know the efficiency of the auxiliary, but the plant we know. So we simply get the value of efficiency of the auxiliary. Then auxiliary, the amount of work being provided, so it will need some electrical energy, right? So that is actually the loss. So amount of work supplied is WC, amount given as in desired effect will be WA. So this will be actually subtracting the loss from the WC. So we will get this kind of relation, and simply by this, so this is the electrical consumption is to the amount of work, electrical power supplied. So that we will get as 77.32% of the net electrical energy generated is consumed by the auxiliary. So here we have finally learned about the cogeneration of power and process heat, and then we have solved a few problems, and I hope that you are more familiar with the TS diagram and how to use Mollier chart than the steam table using this. So I hope that these are will be means you will get a lot of help, I think, from means to solve the problems in your course. So these are the things. Later I have a sample problem, so this will be recorded in the video. You can go through it, and later on I will discuss how to solve this. So this is a very straightforward problem, very straightforward. So there is an economizer, boiler, superheater. So you will just have to estimate the heat transfer per kg of fuel in each component, and the efficiency of the steam generator, then the percentage of total heat absorption taking place in the economizer, boiler and superheater respectively. All the data are given. The unknowns can be taken up from the steam table, so I think there will be no problem, I hope. And if there is, I will solve this problem in the next live session. So this was the my lecture till now. So is there any doubt? Yeah, yes. Ha. So basically what happens is that there will be I square R loss, no? Some amount of electricity will be transformed into heat energy in the machines, and there are also some conversion factors. Suppose there is a transformer, the transformer will also have loss. So in together, how much of electricity is consumed and not being able to show up into the desired effect, that we need as a ratio of the total amount of electricity provided. 2.8 or 2.4? Huh. Okay. Pump work, actually we are not considering the this H4 H5. I think maybe it is somewhat needed. We cannot neglect the pump work. I d- I'm not sure about this. I will go and have a look. But the pump work is obviously needed to calculate the H5 and H7. Suppose if you are not given this to calculate the pump work, then what you can do is that you can directly assume that H5 equals to H4 and H7 equals to H6. So I will give you a quantitative value. Let me give you a quantitative value about this H4. So H4 is 149.79, right? So just remember 149.79, very close to 150. Then I will show you what is H5. So actually it is a misprint. This should be H5. That is 153.8. So only how much? 4 kilojoule per kg. That is quite negligible, right? Again here also you can see the factor 1.061 into 10 to the power minus 3 into the pressure difference. So this is having a very negligible effect on this. I can actually right. So that is why actually you see 504.7 and this is 508, so that is 4 difference. So you see, if you can directly assume that this is the enthalpy at 5, so H5 equals to H4 and H7 equals to H6, still you will get the approximately correct value. Hmm. 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 So actually there is like direct mixing. What happens is normally the waters will be mixed directly and it will be in contact. There will be no indirect means heat exchanger. Okay, so direct heat exchanger. But here what happens is that suppose you supply separate pipelines to the boiler. Okay, so basically what happens, boiler, in a boiler, if we have a this fire tube boiler. Okay, so the flue gases are moving right in a pipe. So if we somehow supply the this water together into that, that will have a mixing effect. Okay, that will not have a this 5 and 7 separately. But if we are talking about fire tube boilers, then what happens is that we are supplying water at different lines, right? So at different lines if we supply into the boiler, then we can somehow neglect this mixing. Okay, this might also have a negligible effect, so we can somehow neglect this mixing and directly go for the difference, overall difference, 1 to 5 and 1 to 7 also. But if you take the difference also now, if you somehow mix it, the pressure difference is not that high. Means 2 bar and 40 bar, that is okay. But the intermediate pressure 2 and 0.06 bar, that is also not that high. If it would have been like 10 bar, then the point, see, if 10 bar is there, then the point would have come here now. So then the enthalpy mixture would have more significance. But the 2 bar and 0.06 bar, I do not think that is quite high. So if you separately send up this water lines to the boiler in a this water tube boiler, then you can separately you can get the steam at this particular point. So it will be a mixture at this particular point. Actually, this cogeneration of power and process heat, this exactly this kind of problem may not come. The means reheating, regeneration, I do not know what kind of problem will come, but some problem will be a little bit tricky. So they will say that this is a TS diagram, you solve it. Okay, then what you say, you will from practical point of view, do not take it up. Do not think that this is a mixture. Even if you take it as a mixture, you consider the pressure difference. If the pressure difference is quite high, just take the mixture. If the pressure difference is quite low, then it will save you some time, that you do not consider this mixture, right? So you can take that into advantage. Mhm. Hmm, hmm, hmm. exact difference. See, from in a pass out turbine, so we as the name suggests, we're passing out something. Hmm. So here you can see that turbine completely ws is not going through the turbine, so some amount of ws minus w is also going. So this is actually contributing to the enthalpy difference out here, and ws is responsible for the between the 1 and 2 energy generation between the 1 and 2. So the energy generation is not uniform. So here the energy generation is less, here the energy generation is more, but in a still we are getting some energy generation, right? But in back pressure turbine, we are not allowing the steam to expand till point 3, not even ws minus w. We are simply allowing some pressure which is maybe at 2 bar, right? So if we want to normally it will expand in 0.06 bar, but we are supplying this 2 minus 0.06 bar here so that it does not expand here. So we are applying some back pressure here. So the net energy generation will be only ws here, and ws1 minus h1 minus h2. So that will be lower amount of energy generation, right? But the thing is that it is quite simple in means in the complexity is very less, also the maintenance cost is also very less. So if you are working in a moderate industries where so much of complexity is not needed, sophistication is not needed, go for the back pressure turbine. If such kind of desired effect is required, then you need to go for some better suitable options like the pass out turbine. Also the turbine, when you pass out the fluid steam from the turbine, there it indulges some extra losses. Normally you won't find a isentropic process, right? There will be some efficiency related, so the process will be like this. So accordingly your whole scenario, the power output and everything will change. Exactly. Not exactly, not exactly. Still, we are not getting the complete potential, right? If WS would have passed from 1 to 3, then it would have given the complete potential. But some amount of W is being passed out from point state 2, right? So the energy generation from this point would have been, you just imagine H2 minus H3 is the enthalpy difference. First, if would I wouldn't have let any steam to pass, so ws into h2 minus h3, that would have been the energy generation from here. Now it is ws minus w into h2 minus h3, so some amount of energy generation from here is less. Still we are getting somewhat near to the complete potential in the pass out turbine. Yes sir. Yes sir, yes sir, right. Okay, okay, thank you for the problem. Is anyone having any more doubts? Then I think we can end this session.